Right, this is an Edexcel paper 2020. It's the Physics Paper 2 triple higher tier. You get 1 hour and 45 minutes in your proper exam and it's worth 100 marks. This is a walkthrough. I'll show you how to answer these questions in case they come up again. Question 1. Figure 1 shows some forces acting on a seesaw. The forces shown have the same magnitude, which means size, but act in different directions. In which of these could the forces acting on a seesaw be in equilibrium, which means they balance each other out? And that would mean that the seesaw isn't moving. So that going down and that going up would mean that it's rotating, so that's not balanced. That on that side and that on that side, yeah, that's the one that'll be balanced. Let's just check these. That going down, that going up, no, that would spin. That going up, that going down, that would spin. So the answer's definitely B. Question B. Figure 2 shows an open door. Explain why it's easier to close the door by pushing at point P rather than pushing at point Q. So basically, a moment, which is a turning effect, equals force times by the perpendicular distance to the pivot. So basically the door hinges are the pivots. So if you push at Q, it's a small distance. If you push at P, it's a large distance. So if this distance is large, it's going to make the turning effect large. So a smaller force would be needed to create the turning effect required. Question C. Figure 3 is a diagram of the forces acting on a swing. The swing is not moving. The seat of the swing, AB, is 0.8 metres long. A person of weight 450 newtons sits on the seat. The person's weight acts at a distance of 0.5 metres from A, as shown in figure 3. Ignore the weight of the seat. The upward forces exerted by the ropes on the seat are F1 and F2. Calculate the force F2 by taking moments about A. Right, because we're taking the moments from A and F1 comes up through A, the moment will equal force times by perpendicular distance, but the perpendicular distance will be 0, so we can basically forget about F1 because it's not going to create a turning effect. So what we're looking for then is the only turning effect we've got is that distance there times by that force there, and that'll be going clockwise. That's a clockwise moment, and that needs to be balanced out by that distance times by that force, because that will create a anti-clockwise moment around point A. And if everything's balanced, then 0.5 metres times by 450 newtons will have to equal 0.8 metres times by F2. So that the anti-clockwise moment equals the clockwise moment. So if we rearrange that, we'll have 0.5 metres times by 450 newtons divided by 0.8 metres will give us F2. So we'll pop that in the calculator, and that's 281.25 newtons. We knew it was in equilibrium because it said the swing's not moving. Question 2, Part A. Figure 4 shows a small piece of copper about 3 centimetres high. A student wants to determine the density of the copper. The student uses a balance to measure the mass of the piece of copper. Explain how the student could measure the volume of the piece of copper. Right, well, if you pop it into a displacement canister, we fill the displacement canister up with water, pop a little measuring cylinder there, and that's empty. And then we will pop in the piece of copper, and as the copper goes down into the water will rise, and because we've got our little measuring cylinder here, the water is going to drip down and it's going to start to fill up the measuring cylinder. And that volume there of water displaced equals the volume of the copper. Part 2. The mass of the piece of copper is 0.058 kilograms, so that's M. The volume of the piece of copper is 6.5 times 10 to the minus 6 meters cubed, so that's V. Calculate the density of the copper, and density is P. So density P equals mass divided by volume, so that's 0.058 kilograms divided by 6.5 times 10 to the minus 6 meters cubed, and that equals 8,923.1 kilograms per meter cubed. Part B. A student wants to determine the specific heat capacity of copper. Figure 5 shows a piece of copper with a thread tied around it in a glass beaker of boiling water. The student leaves the piece of copper in the boiling water so that the copper reaches a temperature of 100 degrees C. The student uses the thread to take the piece of copper out of the boiling water. The student puts the hot piece of copper into a different beaker of cooled water at 20 degrees C. The apparatus is shown in figure 6. The student assumes that the thermal energy gained by the water equals the thermal energy lost by the piece of copper. The water and copper both reach a temperature of 22 degrees C. The cooled water gains 1050 joules of energy. The mass of the piece of copper is 0.058 kilograms. Question 1, or Part 1. Calculate a value for the specific heat capacity of copper using these results. Use the equation. Right. Change in thermal energy equals mass times by specific heat capacity times by change in temperature. Now we need to rearrange that to get the specific heat capacity, which is C. So if we do a quick magic triangle, now there's 4 things, so we'll have to modify the triangle so that we've got 2 multiplied signs on the bottom, not just 1. So it's M times by C times by delta theta. And delta Q, that's the heat energy, goes on the top. Now we're looking for C, so I'll cover up C, and what you're left with, delta Q divided by M times by delta theta. Right, so the heat energy, the cold water gained that much heat energy. So that means that that's how much heat energy the copper lost, according to that statement there. And we need the mass of the copper because we're trying to get the specific heat capacity of copper. And the mass of the copper was that. If it told us what the mass of the water was, just ignore that. It's the mass of the copper that we need. So that's 0.058 kilograms. And we need the change in temperature of the copper, not of the water. because we're trying to get the specific heat capacity of copper. So the copper started at 100 degrees C and it finished at 22 degrees C. So that'll tell us the temperature change of the copper. And when we pop those numbers in, and that is 232.1, and that's joules per kilogram degrees C, which is the correct units. Part 2. The value for the specific heat capacity of copper obtained from the student's results is lower than the correct value. State 2 ways that the experiment could be improved to give a value that is closer to the correct value. Right, let's have a look and see why might it be wrong. So it's lower than it should be. This value here is lower than it should be. So that might mean that the heat was lower than it should be, or the mass was higher than it should be, or the temperature change was higher than it should be. Now they're basically pulling that hot piece of copper out of that water. They've got to move it and dunk it into there. Now it will definitely lose some heat energy on the way across. So that would mean that the amount of energy that they've said, the 1050 that's gone into the cold water, not all of it actually went into the cold water. Or pop a lid on there to make sure that it sort of stays in the cold water. And where that thermometer is, maybe if we stirred the water, that would definitely make sure that it wasn't sitting in a hot or a cold pocket. Plus that glass would have been cold, so some of the heat wouldn't have gone into the water, it would have gone into the glass. So I'll pop down a few of those reasons and you can compare it with what you've said. So reduce the heat loss from the water, add a lid or insulation around the glass. Use a stirrer to get correct temperature. Some energy will have went into the glass. Transfer the hot copper faster. So probably the two that I like the best is that one and that one. Question 3. Figure 7 shows a drone. The drone has 4 spinning blades. The upward force produced enables the drone to rise in the air. The speed at which the blade spins is measured in turns per minute. Figure 8 shows how the upward force produced by the 4 blades depends on the speed at which the blades spin. So as the speed is getting faster, the upward force is getting bigger, but it's a curve, so that's non-linear. Describe the relationship between upward force and speed shown by this graph. Right, well, it's exactly what I've just said. As speed increases, force increases. Non-linear. And that's because it's a curve. If it was a straight line, then say linear. Part B. A different drone has a mass of 4.5 kilograms. That's the mass M. This drone rises from the ground with a height of 20 meters, and that's H. Calculate the change in gravitational potential energy, so GPE is our target, when the drone rises through a height of 20 meters. Gravitational field strength G is 10 newtons per kilogram. That's gravity on Earth. So GPE equals mass times by gravity times by height. So that's 4.5 kilograms times by 10 newtons per kilogram times by the height difference of 20 meters. And that equals exactly 900 joules. You can put a little delta in there for change in height and a little delta in there for change in GPE. Part 2. State the amount of useful work by the blades as the drone rises through 20 metres. So the energy gained will be the work done. So that's basically 900 joules. Now you'll notice it's only worth 1 mark and there's hardly any room here. So the chances are you weren't going to need to do a calculation. So there's a top tip for what to look out for. Part 3. It takes 4 seconds, so that's the time, for the drone to rise through the 20 metres. Calculate the useful power, so that is our target, developed by the blades in this time of 4 seconds. So power equals work done or energy transferred divided by the time. So that was 900 joules divided by 4 seconds. And that comes out as 225. Now that'll be joules per second, or otherwise known as a watt. So that's 225 watts. Question 4. This question is about static electricity. Question A. A student has a rubber balloon tied to a long piece of cotton thread. The student gives the balloon an overall electrostatic charge. So that could be like positive or negative. Part 1. Describe one way that the student could give the balloon an overall electrostatic charge. You want to rub the balloon. So use friction with an insulator, such as a piece of cloth. And that'll cause electrons to be transferred. Now if they'd said the balloon was negative, I would say that electrons got transferred to the balloon, or if they said the balloon was positive, I'd say electrons got transferred away from the balloon. Part 2. The student gives the balloon an overall negative charge. Which of these sentences explains why the overall charge on the balloon is negative? Well, as I've just said, it's because negative charge has been added to the balloon. So electrons have been added to the balloon. Now remember, you can never move the positive charges. They are the protons which are tucked away tight in the nucleus. So it's only ever the electrons in the outer shells that get transferred. Part 3. The student charges another balloon on a long thread. Explain how the student can show that the two balloons have the same type of charge. Right, well you'd have to handle the balloons in a way that you didn't discharge them. So pick them up by the strings. So pick the balloons up by the strings so they don't discharge. Bring the balloons near to each other. They will repel if they've got the same charge. So that's like that. Hang them together like that, and if they got the same charge, then they'll repel away. Question B. Figure 9 shows a plastic block and a metal disc with an insulating handle. The top surface of the plastic block has a negative charge. The metal disc has no overall electric charge. A student uses the insulating handle to hold the metal disc above the plastic block. Which of these diagrams shows how the charge is distributed on the metal disc? So this is what you call an induced charge. The negative charges here will cause the negative charges here to get pushed back, and that'll leave a positive charge exposed at the front. So the answer's B. Part 2. The student keeps holding the metal disc above the charged plastic block and taps the metal disc with a finger. This earths the metal disc for a short time. Explain why the disc now has an overall positive charge. So basically, the electrons flow to the earth. So the electrons flow through the person, and the person provides a path to earth, and the electrons flow down into the earth. Part 3. Figure 10 shows the charges on part of the metal disc and the plastic block. On Figure 10, draw lines to show the shape and direction of the electric field between the metal disc and the plastic block. Right, you need at least 3 straight lines that are equidistant apart. So that means equal distance apart, so the same distance there as what it is there. And the electric field always flows from the positive to the negative. Question 5. Figure 11 shows the magnetic field of a magnet. At which point is the magnetic field the strongest? Well, it's always the strongest where the field lines are the closest. So out of A, B, C and D, that's B. Part B. Figure 12 shows a wire carrying a current. Draw on the card in Figure 12 the magnetic field that is produced by the current. Right, well it's your right hand grip rule. So if you were to align your thumb, so it's pointing the same way as the current, then your fingers would show which way the field's going. Now I'm so sorry, that picture is terrible. I'm not much of a drawer. So the current would be going down and the magnetic field would be in a circle. And it should start off close together and the lines get further and further apart if you're doing it accurately. And you can see if you're looking down on top, the field lines are going clockwise. So you get 1 mark for the shape and 1 mark for the direction of the field. And you need to draw at least 2 circles. Part C. Figure 13 shows 2 metal rods carrying a current. A metal roller touches both rods and completes the circuit. The roller is in the magnetic field produced by a magnet. So there's the magnet and it's inside the magnetic field. The magnetic flux density of the magnetic field at the roller is 1.2 Tesla. So that's B. The current in the roller is 2.5 amps, so that's I. The length of the roller carrying the current is 0.06 meters, so that's L. Calculate the force on the roller, use the equation. Right, we just need to pop the numbers in. So the force equals 1.2 Tesla times by 2.5 amps times by 0.06 meters, and that comes out as 0.18 newtons. Part 2. Describe how Fleming's left-hand rule can be used to determine the direction of the force acting on the roller. You may draw a diagram to help your answer. So I'm going to try to draw left hand. So there's the wrist. The thumb comes up. The first finger comes out at 90 degrees there. And the second finger comes out. So that would be at 90 degrees and that would be at 90 degrees. So all 3 fingers are at 90 degrees to each other. Your other little fingers are tucked away there. To keep it simple, that would be your thumb, that would be your first finger, and that would be your second finger. 90 degrees, 90 degrees, 90 degrees. Make sure you label them. So the thumb equals the movement, which is obviously caused by a force. The first finger shows you the field, as in the magnetic field. Knuckles would be north, fingertips would be south. So the magnetic field always points from north to south. And the second finger shows you which way the current is flowing. And that would be conventional current from positive to negative. And you'll get all 3 marks for that. You don't need to say the bit about north to south, and you don't need to say the bit about positive to negative to get the 3 marks. I just told you that just to make sure you know. Part 3. Draw an arrow on figure 13 to show the direction of the force acting on the roller. Draw an arrow on figure 13 to show the direction of the force acting on the roller. Right, so the magnetic field would be going from north to south, so that's going upwards. So if you put your first finger pointing up, now it says the current's going in here, and it would be going along this metal rod, through the metal roller, out of this metal rod, and then the current's coming out there. So basically the current is going that way. So if you point your second finger in to the board, then basically it leaves your thumb pointing this way. So that's the way that this little roller is going to roll. It's going to go from the left to the right. So if you are using your fingers, your first finger points up, your second finger's pointing that way, which leaves your thumb pointing this way. And your thumb shows you the force, which is what creates the movement. So that's the arrow that you would have to draw, the one I've just circled. Question 6. Figure 14 shows a spring standing on a table. Weights are added to the spring as shown in figures 14b and 14c. A part 1. Estimate the original length of the spring as shown in figure 14a. Right. That looks to be about 52, and that'll be millimetres. So it's definitely bigger than 50 and definitely smaller than 55. And that's actually the range that they'll accept. Part 2. Describe how the reduction in the length of the spring when weights are added can be determined. Right. The compression will just be that original length, and then there's the new length. So the compression will just be the original length, take away the new length. Part 3. State 2 ways that the experimental procedure could be improved. Right, let's go back and have a look at the picture. Right, I know they're millimetres, but they haven't got any little intervals. So if we used a ruler with millimetre divisions and move the ruler closer to the spring, or use a pointer, and if in doubt, just say repeat and average. And make sure that your eye is also at eye level so you don't have any parallax errors. I suppose you could add more weight to increase the range. Looks like they've added quite a lot of masses there anyway. Use a ruler with millimetre divisions. move the ruler closer to the spring. As I say, other things you could say is use a pointer, repeat an average, and get eye level so there's no parallax error. Yeah, add more weights if you wanted. That would increase the range. My two favourites would be that one and that one. Just keep it simple. Part 4. Give one reason why the reduction in length eventually reaches a limit as more weights are added. Right, well that spring's getting more and more squashed. Eventually those coils will actually be touching each other and you won't be able to squash it anymore. The coils will touch and the spring is fully compressed. Part B. A different spring is extended. A force of 0.5 newtons, that's the force, gives an extension of 13 millimeters. So the extension, calculate the spring constant K in newtons per meter. Right, we need to convert millimeters into meters. So 13 millimeters is 13 times 10 to the minus 3 meters. And that's because there's 1,000 millimeters in a meter. So the equation you need is F equals K times by X. So if you were to pop that in a magic triangle, K times by X would go on the bottom, so that would leave F on the top. We're looking for K, cover up K. To get K, you'd have to do force divided by extension. Pop the numbers in. And that equals 38.46. And I'll leave it to 2 decimal places because this number over here is the 2 decimal places. Question C. Another spring is extended. The work done to extend the spring is 0.14 joules. Right, so remember work done equals energy transferred. The spring constant of the spring is 175 newtons per meter, so that's K. Calculate the extension of the spring, so that's X. Use an equation selected from the list of equations at the end of this paper. So the formula you're looking for is energy equals 1/2 K X squared. If we pop that in a magic triangle, we just need to modify the triangle because we need 3 things on the bottom. So that would be 1/2 times by K times by X squared, and that's going to equal E. So we want extension. So we'd have extension squared equals, so if we cover this up, we are left with E divided by 1/2 times by K. So E divided by 1/2 times by K. Now if we pop the numbers in, now remember we're working out X squared, so we will have to square root it. So the energy was 0.14 joules. Divide that by 1/2, which is 0.5, times by K, which is 175 newtons per meter. And that comes out as 1.6 times 10 to the minus 3. And that'll be X squared. So X will be the square root of 1.6 times 10 to the minus 3. And that is exactly 0.04. That'll be meters. Question 7, Part A. Figure 15 shows 3 stages of a magnet moving into and then out of a coil of wire. The coil is connected to a milliammeter. Part 1. Which row of the table shows the deflection on the milliammeter for the 3 stages in figure 15? Right, so going in, they are pushing the north in, the current's going that way. Right, magnet moving into the coil. Well, all 4 milliammeters have been deflecting over to the right. Right, stage 2, magnet stationary inside the coil. Well, if it's stationary, you're not going to get any current. So, right, it could be any one of them according to that first bit, but according to stage 2, you're not going to get any current, so it's either that one or that one. And then stage 3, if you're pulling the north out, so you've pushed the north in there, now you're pulling the north out. Well, if pushing the north in gives you a deflection to the right, then pulling the north out is going to give you a deflection to the left. So it's this one. So your answer is C. Part 2. Give 2 ways of increasing the deflections on the milliammeter shown in figure 16. Right, well, you could move the magnet faster. You could use a stronger magnet. You could actually use more turns or rotations on the coil. That's something else you could have said. Make sure you say turns. Part B. Figure 17 is a diagram representing a loudspeaker. Explain how sound is produced when an alternating current is supplied to the coil of the loudspeaker. Right, well, this alternating current will produce an alternating magnetic field in the coil. Now that coil is already inside a magnetic field. So basically, the magnetic field in the coil is now going to interact with the magnetic field of the magnet, and that's going to produce a force. The coil's magnetic field will interact with the magnet's magnetic field. This will produce a force. And the cone will be moved, which will produce a sound. And basically, because the current's constantly alternating, the cone will constantly be going in and out. The alternating current will produce a constantly alternating magnetic field, so the cone will continuously vibrate to create that constant sound. Question C. Figure 18 shows a transformer. Part 1. State the purpose of the transformer shown in figure 18. Right, so you've got 18 turns on the primary, 26 turns on the secondary. It's a step up transformer, so it'll increase the voltage. Whatever the transformer says it does, that's what it'll do to the voltage. And then consequently, if it's going to increase the voltage, you could also say it's going to decrease the current. Because whatever it does to the voltage, it does the opposite to the current. Part 2. Calculate the output voltage of the secondary coil. Use an equation selected from the list of equations at the end of the paper. Right, that's the formula we want. Voltage across the primary coil divided by voltage across the secondary is going to equal the number of turns on the primary coil divided by the number of turns on the secondary coil. Right, so we need to calculate the output voltage of the secondary coil, which is Vs. Right, what I'm going to do is I'm actually going to flip this. If I flip this left hand side and flip the right, that means I can get Vs on the top. Remember, whatever you do to the left hand side, as long as you do the same thing to the right hand side, they'll still equal each other. Right, now all I need to do is multiply both sides by Vp, and then that Vp will cancel out with that Vp, and that'll leave Vs equals Ns divided by Np times by Vp, and we'll just pop the numbers in. So Ns is the number of turns on the secondary, so that's 26. Np is the number of turns on the primary, which is 18, and then just multiply it by the voltage on the primary, which was 230 volts, and that comes out as 332.2 recurrent. So I'll just put that down as 332. Question 8. Part A. The student investigates resistors connected in parallel using a number of resistors. Each resistor has the same resistance. Figure 19 shows a circuit diagram with one resistor R. Part 1. Add to figure 19 a voltmeter to find the potential difference across resistor R and another resistor in parallel with resistor R. Right, so a voltmeter across resistor R and another resistor in parallel with resistor R. There you go. Part 2. State the measurements that the student must take to find the overall resistance of the resistors in parallel. Right, in order to get the resistance, you're going to need the voltage and you're going to need the current. So measure voltage with a voltmeter and measure the current with an ammeter. Part 3. The student investigates how the overall resistance of the circuit changes when additional resistors are added in parallel to R. Each resistor has the same resistance. Figure 20 shows the results of the student's investigation. State the resistance of a single resistor. Right, number of resistors, well, one resistor will be there. If that's 0 and that's 2 and that's 4 and that's 6, that'll be 1 there. So the answer is 1 ohm. Part 4. Comment on the relationship between the overall resistance of the circuit and the number of resistors in parallel. Use information from figure 20 to support your answer. Right, let's give our statement. So as the number of resistors gets bigger, the resistance is getting smaller. I'm just going to slip the word overall in there. So that was overall resistance. Not that it probably matters. Right, so you'll always get 1 mark for saying your basic relationship. Right, is it a curve? Yes, it is. Right, say it's non-linear. So it's a non-linear relationship. If it was a straight line going down or a straight line going up, say it's linear. And you're going to get your 3rd mark by using information from figure 20 to support your answer. Okay, so we'll say, for example, when we've got 2 resistors, the resistance was 0.5, and when we've got 5 resistors, the resistance was 0.2. So that proves that as the number of resistance got bigger, the overall resistance got smaller. So that just reinforces our first statement about as the number of resistors gets bigger, the overall resistance gets smaller. You could have just used any two relevant values from the graph. So just pick a couple of values where it's easy to see what the resistance was. Part B. A different circuit is then set up with two resistors as shown in figure 21. Right, in series. Calculate the potential difference across the 15 ohm resistor. So potential difference is a posh word for voltage. Voltage equals current times by resistance. So the current going through is 0.2 amps and the resistance is 15 ohms. It's as simple as that. Don't overthink it. So the answer is 3 volts. Part 2. Calculate the total power dissipated when there is a current of 0.2 amps in the two resistors. Use the equation. Right, now you need to add the resistors together. If you're going to get the total power, you need to use the total resistance. Now because these are in series, you just literally add them together. So 15 plus 20 is 35 ohms. So we'll do the current squared, so that's 0.2 squared times by the resistance, the total resistance, that's 35 ohms, and that equals 1.4, and that's watts. If they wanted you to work out the power of just the 15 ohm resistor, then you would just put that resistance as 15. Okay. Question 9, Part A. The magnitude and direction of a force can be represented by a vector. Figure 22 shows the forces acting on 4 identical trolleys. The arrows show the magnitude and direction of the forces. So that's basically what a vector is. It's a quantity with size and direction. Magnitude and direction. Which diagram shows a pair of forces that will produce 0 acceleration? Right, well that's going to accelerate. Right, these are going to cancel out, so that'll be 0 acceleration there. That's going to accelerate that way, and this one is going to accelerate this way. Some of this here will get cancelled out by that little bit there. So remember, if forces are acting in the same direction, you add them together. And if forces are acting in the opposite direction, you take them away. Part B. Figure 23 shows 2 small boats pulling a much larger ship. The ship is connected to the boats with ropes. The tension T in each of the ropes has a magnitude of 20 kilonewtons. So it's the same. The ropes are at right angles to each other. Draw a vector diagram and use it to determine the resultant force that the boats exert on the ship. Right, well I'm doing this on a computer and I've zoomed in. So my measurements will probably be different to yours as you're measuring yours on the actual A4 paper. Now, when I'm measuring this length here on my screen, it comes out as exactly 2 centimetres. And that 2 centimetres is representing 20 kilonewtons. So the scale is basically 1 centimetre is 10 kilonewtons. And when I've measured that across there, that's also the same. So tell them what scale you're going to use. 1 centimetre equals 10 kilonewtons. Now draw a line. That's 2 centimetres long then. Then you'll need to draw a line at right angles. That's also 2 centimetres that way. Then if we took this force here and added it to the end of there, and took this force here and added it to the end there, we've got a kind of parallelogram of forces. Now I know mine's gone slightly wonky there, that's the package I'm using. And then what we're interested in is where did we start and where did we finish? and you're interested in that length there, that's going to be your resultant. So we'd need to measure it with the ruler. Now when I'm measuring it on my screen, it's 2.8 centimetres. So 2.8 centimetres, and for every 1 centimetre it's 10 kilonewtons, so just multiply that by 10 kilonewtons. And that comes out as 28 kilonewtons. So you've basically done a scale drawing to work it out. Or you could use Pythagoras' theorem. That's 20 kilonewtons, and that's 20 kilonewtons. And what we're basically looking for is that length. That length there would be the same as that length there. If I call that A, that would be B, and then that would be C. And obviously C squared equals A squared plus B squared. So C is the square root of A squared plus B squared, which would be the square root of 20 squared plus 20 squared, which is the square root of 800, which once again comes out as 28. And that was in kilonewtons and that was in kilonewtons, so that's going to be in kilonewtons as well. So it just depends which way you like to do it. At A-level physics, we would definitely use the Pythagoras' theorem because it's more accurate. Part C, the 6th marker. Figure 24 shows a wooden block connected to a weight by a string. The string goes over a pulley. The surfaces of the table and the wooden block are both rough. The wooden block moves across the table at a constant horizontal velocity. Several vertical and horizontal forces act on the wooden block as it moves. Explain how the forces keep the wooden block moving across the table at a constant horizontal velocity. Your answer should refer to all the forces acting on the wooden block. You may add to the diagram to help with your answer. Right, that weight is basically pulling down, which is going to create a tension pulling that way. So tension, which is horizontal force. Now if it's moving at a constant velocity, you're going to get friction down here, opposing motion. And the friction must be the same size as the tension. So the friction force equals the tension force because it's moving at constant horizontal velocity. Now vertical, you've got weight going down and you've got a normal contact force going up. And since the block isn't moving up or down, they must be balanced as well. Right, so that's pretty much it. I can tidy that up for you if you want. Tension in string, and that'll be forwards. Friction backwards. Tension equals friction. Balanced forces since constant horizontal velocity. Vertical forces. Normal contact force up. Weight down. Normal equals your weight. Once again, balanced forces since no vertical velocity. And you'll easily get your 6 marks for that. Question 10, Part A. Figure 25 shows 4 identical metal cans, each filled with water to the same level. Each can has 3 tubes. Water comes out of each tube. Which of these shows the correct pattern of water coming out of the tubes? Right, the deeper you go, the bigger the pressure is, so it's going to squirt out further. So the bottom one needs to squirt out the furthest, the middle one needs to squirt out the medium, and the top needs to squirt out the least. So your answer's C. Try it if you don't believe me. Question B. Figure 26 shows a glass U-tube containing water of density 1,000 kilograms per metre cubed. The water levels are the same on both sides of the U-tube. Both ends of the U-tube are open to the atmosphere, right? Just means the ends are open. Atmospheric pressure is 101,000 newtons per metre squared. Figure 27 shows the U-tube with one side connected to a gas supply. So that side there. The difference in the levels of water H is 0.2 metres. Right, so obviously the gas must be pushing in there, and it's forcing this bit of water down and it's forcing that up. It's created this change in height here, H. Part 1. Calculate the gas supply pressure. Use an equation selected from the list of equations at the end of the paper. Right, we need this. Pressure due to a column of liquid equals the height of the column times by the density of the liquid times by the gravitational field strength. So pressure equals the height of the column times by the density of the liquid times by gravity. So the height difference was 0.2, so that's our H value. Multiply that by the density. Density is 1,000 kilograms per metre cubed. And good old gravity on Earth is 10 newtons per kilogram. And that equals 2,000. Now that'll be the pressure difference which is causing the height difference. The units will be newtons per metre squared, or pascals. So if we go back to the original atmospheric pressure, so basically there's atmospheric pressure pushing down on this side, which is 101,000 newtons per metre squared, and this one is getting pushed down more. So the pressure here must be more than that pressure there. So we know that the pressure difference was 2,000. So we need to add that to the 101,000. So basically the pressure over here must be 103,000. So because this is extra pressure pushing down, that's why it's pushing this side up. So your answer is 103,000. Part 2. The measurement is repeated using a U-tube of larger cross-sectional area. Explain why the value of H does not change. Right, so if they're going to change the area, let's look at the equation again. To get the pressure, it's going to be height times by density times by gravity. Therefore, we could rearrange that. So, magic triangle. Put the values in. Now we'll rearrange it to find the height. So the H, the height, cover up the height, what we're left with, P divided by rho times by G. P divided by rho times by G. Now, if they're going to increase the area, is that going to affect the height? No, because area is not in the equation. Height doesn't change as not affected by area, as shown by the equation. Basically, A is not involved in the equation. 2 marks, thank you. So as I always say, base your explanation on your calculation. You'll not go far wrong. Question 10C. The last question, it's another 6 marker. Figure 28 shows a cross-section of a boat floating in water and the same boat with a load inside. The boat floats lower in the water when there is a load inside the boat. Explain why the boat floats in water and why the boat floats lower in the water when there is a load inside the boat. You may add to the diagram to help with your answer. Right, basically, why does a boat float in water? Now what you're looking for is the upthrust is bigger than the weight. Now the upthrust is the difference in pressure between the top and bottom of the boat. Now another reason why they'll float is that the average density of the boat in both cases must be less than the density of the liquid. Now they've said the liquid is water. Now, if it floats, it's because it's displacing its own weight in water. Boats are floating because they have displaced their weight of water. So just say they've got 100 newtons of weight. As long as they displace 100 newtons of water, then they'll float because they've created enough upthrust. Now, because this boat's got a load, it's got a heavier weight, so it needs to displace more water. So that's why it sinks more. So the boat with the load has a greater weight, so needs to displace more water. That's why it sinks lower. In other words, more upthrust is needed to balance the extra weight. And you'll definitely get 6 marks for that. Well, those triple papers always take a while to go over because they're 100 marks. So if you've made it all the way to the end of the video, well done. You will benefit from that. 100% you will, definitely. Keep practicing. The more you practice, the better you get. It's not rocket science, just basic physics. Right. See you in the next video. Work hard, be nice, and bye for now. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained.